just started the recording.
Ah, okay, so you got it.
Okay, so welcome to the more traditional Monday, but on Tuesday seminar this week due to bank holiday yesterday. So it's a pleasure to have Maarten Golterman from San Francisco State University on sabbatical at IFAE this year to talk about Dilaton perturbation theory and application. So thanks a lot, Maarten.
Okay, well, thanks to IFT for the invitation, in particular Gregorio for organizing this. I realized that this is my first in-person talk since COVID started, so I'm very happy to be doing that again because I hate giving talks on Zoom. I hope that I still remember how it goes, so I hope that you are not too unhappy about how it goes. So what I would like to talk about is, well, let's say happy on the title, Dilaton perturbation theory and applications, and I'll explain what this is. This is work together with mostly with Chiral at Tel Aviv University, and the red publications is more or less what I will try to be talking about. And there's a few more topics, some work in progress with a very good student who I have. So basically, I put that on there to advertise his name. So let me begin. Okay. Oh, then we go like. Oh.
The cursor on top of the
Sorry?
of the transparency. Move the mouse on the
No. It worked a minute ago.
Yeah.
No, try now. Try back.
Okay, what did you do? What was the magic?
I just hit it once.
Ah, okay. You always learn. What I would like to do is introduce the reason why we got interested in this first. There's been a lot of collaborations doing lattice physics who started being interested in other theories than QCD. So QCD-like theories. So basically theories with either different gauge groups or we will still take the same gauge group. So it's still SU3, but with a different number of fermion representations or flavors. And what I'm talking about here is, and that's not quite readable, the spectrum of SU3 gauge theory with 8 fundamental flavors. So that's a lot more than in QCD. And of course, there's some beyond the standard model interest, but my interest is really to understand these theories because there seems to be a different behavior. It's not a scaled up version of QCD. And so you want to know whether you can understand more of how that works. Okay. Of course, the fact that there's so much interest on the lattice in these other classes of theory is that one of them may be relevant or not for composite Higgs models or things like that. But that's not what I will be talking about. No phenomenology beyond the standard model phenomenology in this talk. So if you look at this is the spectrum of this theory. The black points are the pions. The green points are the 0++ scalar, which is hard to measure on the lattice. I will not go into the reasons for that, but that's why the error bars are large. Then there's the rho, there's the actual vector, there's the nucleon. And here these are plotted in units of f pi as a function of the quark mass in the theory, again in units of f pi. Okay. And so this is the typical type of plots that you see, spectrum plots. Okay, but the things that are very different from QCD is, first of all, that there's at least at these fermion masses, there seems to be a 0++ scalar in the theory with approximately the same mass as the pion. So this is a stable 0++ state, and we don't see that in QCD. Okay, so there's a light scalar that for the rest of the talk I will refer to as the Dilaton. Okay, but
the sigma is pretty low.
The sigma is pretty low, but the sigma is unstable. It decays into 2 pions, and in fact, we think that if our assumptions as to why this guy is light are indeed true, and which is what our effective theory describes, then you can show that this does not apply to QCD. I can go back to that at the end if you're interested. The other thing that you see is that all of these masses expressed in units of f pi are basically constant as a function of the quark mass, and this is again expressed in units of f pi. Okay. And that is something you again don't see in QCD. In you see the pion, goes basically like a square root of the quark mass, and also, the nucleon have a distinct quark mass dependence. Okay, and so that looks like a version of hyperscaling. But basically, all hadronic scales in this theory, right? This is expressed in units of f pi. So the fact that these are constant basically means that f pi and any of these hadron masses scale in the same way as the function of the quark mass, and that's again something you do not see in QCD. Okay, and so that's what I call approximate hyperscaling here. And then something that this plot does not show, these simulations were done with staggered fermions, and I'll come back to that in one slide, somewhere later in the talk. Have something called phase splittings, and those phase splittings again behave very differently in these theories from the way they discuss in theory. If you don't know what staggered fermions are, don't worry about it. It's just another phenomenon that's different in these theories with 8 fundamental flavors than in QCD. And you see similar behavior in other theories, SO3 with 2 sextets. Okay, and so approximate hyperscaling is usually associated with approximate hyperscale symmetry, and that will be sort of the theme of this talk. So what we would like to do is we would like to set up a low energy effective field theory that describes the pions like you do for QCD, but obviously that low energy theory will have to include that 0++ scalar as well, because it's degenerate with the pions, so you cannot exclude it from your effective field theory. Okay, so I will talk a little bit about behavior as a function of the number of flavors of these gauge theories. I will basically give you a cartoon sketch of what might be happening. Of course, we are using the lattice to really understand what's going on. So, and then I will argue that what might be happening here is that you're close to the conformal window, and that approximate scale symmetry starts setting in, and that's the symmetry that explains why there is a low 0++ state in the theory. And then we're going to use that assumption to build an effective field theory, which is basically chiral perturbation theory with the dilaton added. And that's the thing that I call dilaton chiral perturbation theory. Okay, I'll argue that like in chiral perturbation theory, there's a power counting and a systematic expansion based on these assumptions of approximate scale symmetry, and so that we can use this as a systematic effective field theory. And then I will discuss basically the 3-level results. I will try to use this to explain this hyperscaling behavior fits to these data and see how well this works. Okay. And then I'll hopefully have time for a few comments at the end. Okay. Okay, so here I'm going to show you one possible scenario as to how these theories may behave as a function of NF. And this, I want to stress here, this is a cartoon. This is just a little story to kind of get motivated as to what might be going on. And there are other scenarios. This is not the only possible scenario as to what might make theories walking. Okay. So what I plot here as a function of G squared is the beta function and each of these curves represent different numbers of flavors. And so this is just a 2-lobe beta function. So that's already what makes this a cartoon, of course, because I cannot extend this to literal large coupling. And so for NF equals 2 and 3, so the beta function is negative, goes more negative, and it just all this is asymptotic freedom, and then the coupling always gets strong enough to cause chiral symmetry breaking. Okay, but then we also know that if you go up in the number of flavors, at some point the second coefficient of the beta function changes sign, so this thing starts curving upward, and there will be a 0 somewhere at a very large value of the coupling. Okay, and that 0 moves in if I go to higher number of flavors until I lose asymptotic freedom above NF equals 16. Okay. That means, so that's one half of the picture. The other picture, the other cartoon part of the picture, is that if you look at a gap equation for chiral symmetry breaking, okay, we see that chiral symmetry is broken in the simplest type of gap equation type of approach. Chiral symmetry is broken when the coupling becomes as strong as this value. This is this is the second Casimir. If you substitute it in, it's just pi squared for SU3. So that's a value that we believe that chiral symmetry breaks, at some value of the coupling. That in this simple gap equation approach, it's just a straight line, but it can be a little bit wiggly. But the point is relatively independent of the number of flavors. Okay, and so now 2 things can happen. When your coupling, you start at very large scales, your coupling becomes larger if you're going down in scale. Okay. And then it hits chiral symmetry breaking. Of course, then fermions start with decoupling, so the beta function changes its behavior. Okay, But what may happen is that if you go up in NF, okay, that the coupling reaches an infrared fixed point before you hit chiral symmetry breaking. Okay, so what happens in this plot, in this cartoon, there will be a prediction that the theory qualitatively changes its behavior from a theory that breaks chiral symmetry at low energies. It goes to a theory that has an infrared fixed point and therefore conformal behavior deep in the infrared at a value of NF close equal to 12. Okay, the 12, of course, is again a result of this cartoon, and there are pretty fierce. People try to find this out where this so-called conformal sill is in simulations, and this is a pretty contentious subject, and I'm not going to get into that. Okay, what I'm going to assume for the purpose of this talk is that NF equals 8 is below the sill. Okay, that it does break chiral symmetry at low energies, but that the beta function stays relatively small. Okay, until you hit chiral symmetry breaking, so that this becomes what's called a walking theory. Okay. And so there's a critical value of the number of flavors where you go from a theory that is chirally broken in the infrared to a theory that is conformal in the infrared, and that coupling will G star, okay, and the number of flavors where that happens, which in this plot, in this cartoon plot, could be close to 12, okay, I will call NF stars.
So in the chirally broken one, as the mass goes to 0, there will be a boson.
Yes.
And it will go with the square root in the same way as it gives me.
Yes, I'll come to that.
But
So yes,
that will only be show up very close to the
yes, that's exactly right, and I should recover that from my effective field theory, and we will see that happens. Yeah, exactly right. Okay, so our effective field theory is going to have to contain. So you're assuming that NF equals 8 is below the conformal sill, but not much below. So it's a walking theory, but it breaks chiral symmetry in the infrared. So the theory has to contain the usual pions, which become masses for when the quark mass is taken to 0. Okay, and then the other assumptions that we're making is that if you get close to this conformal sill, so your number of flavors are such that the beta function remains very small all the way to the infrared. Okay, that scale invariance gets restored as you get closer to the conformal sill. Of course, inside the conformal window, scale invariance is restored in the infrared because you're at an infrared fixed point. Okay. Now, one problem that we have is, of course, that our parameter NF, unlike the quark mass that governs the mass of the pions, NF takes discrete values. So, for technical reasons, to just make it simpler to think about it, we're going to make NF a continuous parameter by taking the large N limit in the Veneziano version, where you send NC, the number of powers and the number of flavors, to infinity, keeping the ratio fixed. Okay, but that's to be able to talk about our little NF as a continuous parameter in this game. Okay, and then what we're assuming is that as you approach the conformal sill, and if you're not too far away from the conformal sill, that the theory contains a dilaton, which is this particle that is degenerate in the simulations with the pions. Okay, that's basically a pseudo Nambu-Goldstone boson associated with the spontaneous symmetry breaking of approximate scale symmetry. Okay, which again, this guy would become masses. First of all, of course, if I take the chiral limit, otherwise this sets a scale, and if I take my number of flavors, to go to the limit of the conformal sill. And there's lots of technical issues that I'm not going to get into this talk, just simply because that would take too much time. But so the way that works. So again, this is the continuing of the last slide, basically. So m pi squared. So when m gets very small, as Tony already said, m pi squared should go like the quark mass as usual. And then, of course, scale symmetry is associated with the dilatation current, which can be written in terms of the energy momentum tensor like this. And then there's the well-known trace anomaly that if you look at the divergence of the rotation current, that's equal to the trace of the energy momentum tensor, just hitting this with a d mu. Okay, and of course this trace is non-zero if you have a scale in the theory, like the fermion mass. But there's of course the scale in the theory that you get two-dimensional transmutation. And a long time ago, Collins and Chopra showed that there's this anomalous part of the trace of the energy momentum tensor, which is proportional to the beta function, right? And so our key assumption is going to be that the beta function when you get close to the conformal sill, okay, well, let me go back to that plot. This beta function, this is the distance of the beta function away from the conformal sill when you hit chiral symmetry breaking, and that when you're close to the conformal sill and you're moving into it, okay, that the trace anomaly goes to 0, okay, and that means that in this word identity, if you also take the chiral limit, that the dilatation symmetry would get restored, okay, and that is 0 plus plus state that we see in the simulations, like that's the thing that we have to explain, that is associated with this restoration of scale symmetry, okay. So this thing that breaks scale symmetry in this picture is proportional to the distance from the conformal sill. Of course, it's also non-zero if you take the quark mass non-zero. And then since we're using this Veneziano expansion, so there's a technical issue that there's a 1/NC here. Okay. So what we would like to have is a systematic expansion in the quark mass, like we have a standard dChPT, this distance to the conformal sill, and p squared, which is the, if you look at processes with the typical momentum p, like pion scattering and so on. So n and p squared are the usual expansion parameters of dChPT, and this additional expansion parameter is on top of that, to explain the masses, the close to masslessness of this dilaton. And so this will be the expected behavior of the dilaton mass squared. By the way, we don't know that it's linear in NF star. Nothing in our analysis would change if I assume that this is some power, some positive power. The only thing that we need is that it goes to 0 when NF goes to NF star. Okay, so then in all the formulas, if this is some power not equal to 1, then in all the formulas and the rest of the talk, you just have to put in that power. It doesn't change the analysis. All right, so then let's get to building an effective field theory for this. So the way you usually do that is that you look at your bare lattice theory, you introduce spurions. So instead of having this quark mass n here, I'm allowing for a spurion that transforms on the chiral symmetry, so that this whole Lagrangian is completely invariant on the chiral symmetry. Yes.
The fact that you have chiral symmetry is because there is a gap,
yes,
between a sector which is almost massless and another sector. And this, in this case, it contains also the scalar. So it's
yes,
the scalar and the pi both. No?
so it's this picture, right?
Yeah.
There's this gap, right? So if you ignore the green points, okay, then it will be just the usual gap between pions and all the other states. Okay. And now there's these green points as well, so I have to include those in my effective field theory, but there's still a gap in the rest of the spectrum.
A scalar and
right. Okay, so this is the replacing the quark mass by a spurion that transforms on the chiral symmetry like this. So this is the left-handed and the right-handed part of the flavor group, is standard. Likewise, if I, for instance, use dimensionalization, right, I have to use a regulator in order to see the scale that governs the trace anomaly. Okay, so if I use dimensionalization, then of course this Lagrangian lives in d dimensions. So to make the action invariant under scale transformations, I have to introduce a spurion like this that indeed you see in d equals 4, formally disappears. Okay, and so this whole Lagrangian will transform with lambda to the 4th if I put in this spurion transformation rule, so that the action is invariant under scale symmetry. Okay, and so so the Lagrangian then transforms like this. Sorry, I said lambda to the 4th within d dimensions, of course, it's lambda to the d. Okay, and then you fix, your spurions. You set your chiral spurion equal to n, and sigma back equal to 0. You recover all the explicit symmetry breaking. Okay, but so you use the spurions in order, as we will see on the next slide, to build your chiral Lagrangian. Okay, so then you introduce the effective fields in your effective field theory that will describe the states that you want to include in your effective field theory. So there's the usual pion fields that appear nonlinearly in the chiral Lagrangian, the usual Coleman-Westomino picture. This field transforms like this on the chiral symmetry, so that's completely standard. Okay, and so basically what you notice here is that the effective field transforms like the corresponding spurion. And like that, since we now want to include this dilaton in our chiral effective field theory, we also introduce a dilaton effective field that transforms like its corresponding spurion. Okay, so this is the spurion, this is the effective field and they transform in exactly the same way under scale transformations. Okay. And of course, the spurion, this is 0++ state, so it doesn't have any flavor, it doesn't have any, it's trivial under chiral transformations. Okay, so then we basically, how do you build the chiral Lagrangian? You basically write down the most general operators in an expansion, in a derivative expansion, okay, in terms of these effective fields and the spurions. Okay. So these two terms you will recognize. This is the kinetic term for the pions, like you have in standard chiral perturbation theory. Here's the mass term, where of course once you have so this term is invariant because sigma and chi transform in the same way. Then once you, so this is invariant like the underlying theory once you have introduced the spurions. And once you're done, of course, you set chi back equal to n. Okay. And then of course there's a kinetic term for the dilaton. Okay. These e to the 2 taus here are needed. You know, you can basically verify. It's a very simple the transformation rules that I gave you on the previous slide. That this whole Lagrangian transforms, you know, to lambda to the 4th times itself as it should under a scale transformation. But then, because these the key point here is that because the spurion for scale symmetry and the effective field for the dilaton transform in exactly the same way, their difference is invariant. And so you have arbitrary potentials multiplying each of these terms here. Okay, so this whole Lagrangian is invariant when I transform sigma and chi and the fields as they should under chiral and scale transformations. Okay. One technical point is, of course, that once I go to the effective field theory from the previous slide, I started with my bare Lagrangian with the bare quark mass here, okay, which transforms with its canonical dimension, okay, on the scales, on the scale transformations. Like here, okay. Of course, once I have gone to the effective field theory, I have to renormalize the theory first. So now my chi has become the renormalized mass field, in fact. So the mass picks up an anomalous dimension, so that this picks up an anomalous dimension on the scale transformation, and that's why this gamma star here, where this gamma star is basically the anomalous dimension, the mass anomalous dimension at the infrared fixed point, okay, because everything else should follow from an expansion around the infrared fixed point. And so we have this invariant potentials. And so as long as we have those, of course, each of these potentials you can think of in terms of a Taylor expansion in their argument. Okay, so that has an infinite number of parameters in it, an infinite number of low energy constants. But at this level here, the theory doesn't have any predictive power yet, right? Because this is at order p squared in the power counting. There's 2 derivatives here, or there's 1 power of the mass. There's of course also a Dilaton potential term. So again, if this does not transform, this transforms with the usual lambda to the 4th. Okay, so this, you have basically no information on this potential at all. And so at this point, this theory is not yet useful, not an effective field theory. Sorry? So I'm basically factoring, b tau is a parameter like b pi. So basically it gives me the right dimensions here. So I factored out, you know, this is the usual at pi squared. You would see in chiral perturbation theory, this is the usual at pi squared times the b pi of Gauss-Leutwiler. And then I do similar things here for the kinetic to make these potentials dimensionless. Okay. So those are basically just definitions of low energy constants. All right. So this slide summarizes a lot of math that I'm not going to make you suffer through. So this is again going to be a cartoon version of the argument that we made on our paper, how we organize the power counting for these potentials. Okay. So let's go back. So of course, the way that you construct an effective field theory is always by matching correlation functions in the underlying theory and the effective field theory. That's the name of the game. That's how you construct an effective field theory. So let's go back to our microscopic theory, the underlying theory. Okay, the renormalized microscopic theory, I can expand in powers of sigma, that is the spurion for scale transformations. It had the linear term, of course, is what couples to the trace anomaly. Okay, and then the higher order terms that I will need in the argument. Okay. And if I take one derivative, so what I really should look at is correlation function. So I'm going to make this argument very crude. I'm just going to look at the Lagrangian itself, okay, but see that as a stand-in for looking at all the correlation functions in the theory to all loop order, but it takes a lot of work to go through all of that. Okay, so if I take the derivative of in the microscopic theory with respect to this spurion source, okay, then I of course pick up exactly the trace anomaly, okay, and so that thing by assumption is proportional to the beta function, which I assume to be small. Okay, so if my number of flavors is large enough that I'm close enough to the window sill, this inserts an operator that is proportional to that small parameter. Okay, and of course, if I take multiple derivatives, then I get that parameter to the nth power. Okay, so now let's see how that carries over to the effective field theory. In the effective field theory, and again, let me just take one of those potentials, for instance, this potential here. Okay. And let me take derivatives with respect to sigma. Those I have to match to those derivatives with respect to sigma in the underlying theory. Okay. And if I set up a Taylor expansion for any of these potentials like this, then taking the nth derivative with respect to sigma, of course, projects out that coefficient. Okay. And so then matching this derivative to that derivative tells me that Cn is of order that small parameter to the nth power. Okay, so what I see is that the successive coefficients in the Taylor expansion for any of those potentials are proportional to, so Cn is proportional to a small parameter to the nth power, and that means that if my assumption is that this governs the proximity to the window to the conformal cell, that if this parameter is small, then Cn is suppressed by that small parameter to the nth power. And that means that to any order that I work in the effective field theory, I'll have to expand this only to a finite order. Okay. Now, again, I said this is a cartoon version of the argument because, of course, what I have to do is I have to worry about, first of all, I should not just worry about derivatives of Lagrangians, but I should worry about derivatives of all correlation functions. I should worry, if I apply several derivatives with respect to sigma, one of them can go here and the other one there, go like the nth, C of n goes like the nth power of the small parameter, the new small parameter, the distance to the conformal window. So that means that in this order p squared term, I can just take the lowest order coefficient in that potential, so C0, which I can absorb into the definition of f pi squared, so that potential is gone. Okay. Same thing for the kinetic term, which is order p squared. Same thing for the mass term, which is already order p squared because it's of order the quark mass, which counts the same power in the Chiral counting. Okay, and then here I have to keep two terms, C0 and C1, okay, because C0 is ordered this distance to the 0th power, okay, and C1 is that same distance to the first power, and I'm going to the first power in my set of small parameters here. Okay, then I can shift. So here I don't see a C0. What I did is I shifted the expectation value of the tau field such that C0 is equal to -1/4 times C1. I can always, if I have a potential like this, I can always shift the tau field to make it equal to this. And so what the classical vacuum now is such that I took that value C0 to be 1/4 times C1, such that if you now calculate the expectation value of the Dilaton field by taking the minimum of the classical potential, that's equal to 0 when the quark mass is equal to 0. Okay, so that's just a redefinition of the field that I can always do. Okay, so in principle, I can study this theory as a function of the quark mass and as a function of the number of flavors. Now, changing the number of flavors in simulations is very hard. Okay, these are very expensive simulations because this is with dynamical fermions and this is a lot of fermionic degrees of freedom. Okay. So the hope is, of course, that this theory is helpful in predicting things as a function of the quark mass. And for instance, explain that plot that I showed you on the first slide as a function of the quark mass at fixed NF. Okay, so I'm interested in studying this theory as a function of the quark mass. And so this is why I'm choosing this potential, this shift such that the expectation value of the Dilaton field is 0 at 0 quark mass. And then we'll see how things change if I change the quark mass. Okay, so what I can do
some kind of routing to also.
Fermions in the container.
Yeah, I need to tune
which
number of flavors. You want to make it.
Oh yes, yeah, but still.
That's what I mean.
Yeah.
And you can put in the routing. You can
Yes.
use this parameter somehow in the determinant to make small variations.
Yes, but to, for instance,
I
go,
don't know, maybe it's.
but you still would have to, for each value of NF, you would have to, maybe for very small, maybe go to 9 or 7, you could do some type of re-weighting and make it cheaper than doing a full new simulation. But for instance, if you would want to do it for NF,
I
because
mean, if it makes sense to have some kind of continuum NF by doing the typical thing that.
I would worry about re-weighting, because if you, for instance, want to, suppose that you want to use this to find the conformal sill, it's basically some type of phase transition, and then re-weighting becomes more dangerous. So in principle, you should do new simulations at every value of NF, whether you do it through looping or not. And so each simulation is an expense.
NF doesn't make much sense. In the real world, NF is just a discrete, as you said.
Yes. But so even if I would want to do NF equals 9, 10, 11, I would have to do a new simulation for every NF, and this is very expensive. And re-weighting could become very expensive if the qualitative behavior of the theory is changing. Okay, so now I have my putative effective field theory at lowest order. So this is at order p squared, in this power counting. So I'll say order p squared, but I mean order p squared m, or this distance to the conformal sill. And so now I can look at 3-level predictions. And of course, the first thing that I should do is I should look at the expectation value of the Dilaton field, the minimum classical potential, as a function of the quark mass. It's easy to see that if I take the quark mass positive, that the potential is minimized when I set this called sigma equal to 1, right? So no expectation value for the pion field, no breaking of flavor symmetries. And so I set this equal to 1, and then this becomes the potential for the Dilaton field tau, which I can minimize as a function of m. Okay, so that gets me this equation. So this is what minimizes, the classical potential, where this capital M is a mass scale that just combines all these low energy constants that you see sitting here. You get the pion mass as a function of the quark mass and that expectation value. What you see is because of scale symmetry, there is factors of e to the 2 tau sitting everywhere, and there's this anomalous dimension creeping up here. Okay, so that means that once you have minimized your potential, you substitute the expectation value for tau here. So everything else, like the pion mass squared that you would read off from the mass term here, becomes a function of that v, which is a function of m. Okay, so this is why you start seeing these factors of e to the v showing up here in all predictions. For instance, also f phi, the physical f phi is the f phi in my Lagrangian times e to the expectation value of the Dilaton field, which becomes a function of m. Okay, so something that already is qualitatively changing here is that through this v here, for instance, f phi becomes dependent on the quark mass at 3 level. Right? In QCD, this factor would not be here, so the 3-level prediction will be that f phi is just a constant, right? And mass dependence only comes at order p to the 4th, at the next order in the expansion. Okay. Of course, this parameter, so in my power counting, C1 here is proportional to the distance to the conformal sill. That's the small parameter that governs, the mass of the Dilaton. Okay. With m and C1, I can both vary. So I can look at a region where this ratio is relatively large. I can look at a region where this ratio is relatively small. Okay. And the first thing that I should do is check what Tony already asked about, okay, which is what we call the small mass regime. Right? So if you take the quark mass, so C1 is fixed, right? As long as my number of flavors is fixed, it's fixed because it's just the distance to the conformal sill. But I can take the quark mass to 0, okay? If I take the quark mass to 0, okay, then this thing goes to 0. That means that V here goes to 0, okay? And so that means that all these exponentials here go to 1, and you just recover standard chiral perturbation theory that the pion mass is proportional to the square root of the fermion mass. So you recover this, and the Dilaton mass just goes to a constant, right? Because of this thing, and then again, this e to the v just becomes 1, and this thing becomes also 1, okay? So there is a limit at fixed NF where the pion decouples, or the Dilaton decouples from the theory, and the pion becomes massless if you make the quark mass very small. We can also look at the large mass regime. So there's also a regime where this ratio is relatively large, okay? Then if this ratio is large, then the exponential here is going to dominate. So I can solve this equation, it's a tangential equation, so I cannot solve it in closed form, but I can solve it, it's dominated by the exponential. So I can make for large left-hand side, I can basically ignore that factor v here. It will become a logarithmic correction. Okay. So if I ignore the v here, then I can solve this. And then this factor e to the v here just becomes proportional to the quark mass to the power 1/1 plus the mass anomalous dimension. Okay. And then if you go back to the previous slide, you see that every mass scale here has this factor e to the v in there. This mass squared, this is a mass squared, it has an e to the 2v. If I write the, oh, I don't have that equation here. I should, yeah, here I have. I can, using this equation, I can write n pi squared also in terms of C1 times another factor e to the 2v. So all mass scales in the theory go like a factor e to the v. The e to the v is just this fractional power of the mass. And so this shows that this is this hyperscaling, right? That means that if I look at mass ratios, the mass dependence drops out, and that explains that plot that I showed on the first slide. Okay, so in this case, if I take this mass large, and this is not a big surprise, right? Because M breaks conformal symmetry. C1 is the distance from the conformal window, so it also breaks scale symmetry. And so, but if M dominates, then it's the mass deformation that dominates the breaking of conformal invariance in this theory. Okay, so then basically the theory behaves like a mass deformed conformal theory, and that is what you see here. In a mass deformed conformal theory, hyperscales, right? All masses go like the same power of the one parameter that sets the scale of the breaking of scale invariance. Okay. An important question to ask is that I think skip. So this in the effective field theory, it's a free parameter, but in principle, so by fitting, I will talk about that. By fitting to data, you will be able to determine it. So that will be a way. Yes, people have been trying to measure this. Okay, and so we have our own measurement of it. And no, it's larger. So in this theory, it's more like probably like 0.9 or so. Okay. So relatively large mass anomalous dimension. Okay, but I'll talk about that a little bit more because that is not completely settled. Right? That actually comes to some of the open problems that I wanted to mention at the end if I have any time. By the way, I completely lost track of time now, so you have to tell me that. So let me look. One thing if all mass scales in the theory behave like this power, you might worry whether you still have a gap in the theory, whether the pions and the dilatons are still lighter than all of the other masses. And they are. For instance, if I look at what should be the root expansion parameter in this theory, which in perturbation theory is pi squared over 4 pi f pi squared, right? If I use this formula and that formula, and I look at n pi squared over 4 pi f pi squared, I get something that goes like C1 times V. V is basically the log of this mass ratio here. Okay. And so if C1 is still a small parameter, then it's still a small parameter, right? The only thing that we should require is that this log, right? I'm here in the regime where this left-hand side becomes relatively large, okay? So if this log becomes so large as to undo the smallness of C1, that's when I start getting out of the regime of the chiral effective theory, right? There should be some values of the quark mass where you just lose, control in the effective field theory. But notice that this small parameter only depends logarithmically on the quark mass. So this is a systematic expansion what I'm doing, as long as this combination is much smaller than 1. In QCD, this is the typical mass scale. This is this combination of low energy constants that sets the mass scale in QCD. So M has to be small compared to that mass scale, okay? And here it only logarithmically depends on it. So here is what we call a large mass regime, where this ratio can be large while this parameter is still small, so that I control my effective field theory. And in that large mass regime, I have this hyperscaling that we saw in the plot on the first slide. Okay, so what I'm going to do is I'm going to fit some data, right? Particularly those data that I showed from the LSD collaboration on the first slide. So now we have an active effective field theory. They have measured these quantities, basic quantities at 5 different quark masses. So I can try to do fits, using tree-level Dilaton chiral perturbation theory. Okay. So I'm going to go back to using the exact expression. It's only in the large mass regime that I have hyperscaling, but this theory predicts corrections to that. Okay. The simulations have only been done, unfortunately, at a single bare coupling. So I don't have any control of lattice spacing artifacts. So I'm going to assume they're not there, but this is an assumption I have to make. Again, these simulations are very expensive. I wish they did another lattice spacing, but we will see whether that ever happens. Okay, and then I have to do this fits. And so what I will be fitting is these quantities, m pi squared over f pi squared, f pi in lattice units, and then tau squared over f pi squared. And so these are the functions that we're fitting to. The details are not important. This is f pi in the Chiral limit. In the Chiral limit, v went to 0. So this is f pi in the Chiral limit. Okay, and these other d1, d2, d3 are just linear. They're combinations of those lower order constants. So the details here again are not important, but this is what we fit. So here are the fits of those three quantities. So this is m pi squared over f pi squared. This is a times f pi. As I said in the beginning, the dilaton is a difficult one. The 0 plus mass is hard to measure on the lattice because of disconnected, quark disconnected diagrams. So they come with larger errors. Okay. And we do these fits. These are the range of quark masses on the lattice. So these are the bare quark masses in that simulation. We fit it with the full range of 5 masses and with just dropping the highest point because it's possible that the highest masses are so large that I'm getting outside the range of 3-level chiral perturbation theory. And then, so this is what I show here is fits with the 4 lowest of these 5 masses. So excluding this point, but up to 0.0075. And you see that indeed f pi is a little bit aside the curve. So the 5 mass fit also works pretty well. And so the main result is that we get this in mass anomalous dimension, which has this value. And if you include that point, it doesn't change much. Yeah, so it actually, yeah.
1 plus 1.
Okay. Yes. So basically that critical exponent is equal to approximately a half, okay, from these data. Okay. Of course, there are lots of caveats. I'm using 3-level Dilaton chiral perturbation theory. I'm not including scaling violations because I don't have the information to do that. Okay. So this is just the first attempt to look at these data and see what we get. But that's why this is only a fit error. This is not, that doesn't include systematic errors. I'll say more about that. There's another group that we did the same simulation of 8 fundamental fermions in SU3. It's the LAT-KMI collaboration. LAT-KMI is what it says here. Okay, they simulated the same theory, but with a different lattice action, a different bare coupling, and a different mass range. And that mass range, if you take the values literally, is higher in mass than the LSD scales. But of course, because it's different lattice actions, I cannot directly compare, the lattice spacings here. In that case, so this is a very wide range of masses, and it goes to even higher masses than the LSD collaboration. And in that case, it's very clear that if we want to fit the full range, we cannot do that with 3-level Dilaton chiral perturbation theory. So we may need higher orders. Okay. At higher orders, we constructed the full chiral Lagrangian at the next order in this expansion. It has very many parameters. It has of order because it's not only the higher order parameters that you would get in chiral perturbation theory, but there are more parameters because there's also the Dilaton field around. Okay, so there's no hope that with this limited data we're going to be able to fit those parameters. So we have to kind of guess what is the most important thing. Some of those parameters are going to make the mass anomalous dimension be a function of the mass, right? So far we were able to just fit this gamma star, which is just a fixed parameter at leading order in the expansion. At higher orders, it will become a function of n. We guessed, so it's kind of a model for what happens at next to leading order. And again, we cannot do better because we cannot fit all these higher order constants. What you can argue is that this still said that our choices as to what we resummed, including the resummation, still satisfies the Takahashi identities for scale invariance. It gives a good description of the LAT-KMI data. Okay. In this case, so here we are finding that the mass anomalous dimension depends on the quark mass. So it starts, changing as a function of the scale, which is what you expect, of course, at higher orders. And so let me see that if we include, so we played lots of games. Okay, you can include either only this term and not that term. You can include both terms. So I show 2 of those fits. The magenta band is where we set this parameter equal to 0. So we introduce fewer higher order parameters. We fit 8 out of the 10 masses that they have in this range, and you get this fit for gamma as a function of m. The blue band is when I also include that term, then I can allow myself to go to even higher masses in the range, and I get this fit. Of course, the lat k my data are in this region where they beautifully overlap, right? That's this region. I know lat k my data, otherwise we would know which one of these would be the truth. And the gray band here shows that value of 0.94 that we got from the LSE data, which are at a lower range in the scale. Okay, so this tells us that we don't have enough data to really sort this out, right? And that's just the limitation of the data in these very expensive simulations.
The assumption is that these 8 flavors is just below the conformal.
Yes, that's the assumption.
That we are really there. No?
Right. And I'm going to again say something about that. So that's so far the assumption, right? That we see pions, so there's chiral symmetry breaking. And so that's why that's the basic reason why we assume it. But then we
there are
want
a range of masses where you start seeing the change in behavior for small masses.
So
I mean, that you should see a change in behavior, as we said before, when the mass is very small.
Yes,
to the regime.
that we have not seen. So what we would claim that if Dilaton chiral perturbation theory describes these 2 data sets, they're all in the large mass regime. And so it will be
no small mass.
To reach the small mass regime will be very expensive.
Very difficult. No?
Because you would have to go into much larger volumes.
Yeah.
Right. So that's
the general problem of this quasi-conformal theory.
right. Yes.
There is another question. Sorry.
Yeah, go ahead. Yeah.
You can also do this with adjoint fermions and NF=1, because there you are also supposed to be very close, but below.
Yeah. So this is SU2, right? I think, or
no, SUN and any n.
Any
Adjoint fermions.
So
And in the adjoint fermions, you don't have to tune the NF does not depend on n, because they 2 scale the same way, because it's also adjoint, the gluons and the quarks.
Right.
It's
So
also, I mean, you can do conformal.
So
in this case,
what you would have to assume that our theory applies to that, because we use the Veneziano limit. So the Veneziano limit doesn't work in those theories. So for instance,
you should have to redo it, but in principle.
Yes, but you could say, well,
there's no Veneziano limit there, because
right.
I mean NF.
Right.
I mean, you can only go up to NF=0, so then you are already not asymptotically free.
So
you only have 1 and 2.
Yes. Yeah.
So
and so another theory that has been simulated is SU3 with 2 sextet fermions. And so again, it's just 2. You don't get to go to, and this is the group of Julius Kuti et al.
Sure.
And they have looked at how so Dilaton chiral perturbation theory is consistent with the data. I mean, I don't think Julius would say that it proves that Dilaton chiral perturbation theory is right, but you know, you can see that it seems to work there as well. Now, without excluding that other things might also work. So you know, it's not a claim that nobody's claiming that this is proven to be working.
Many of these people are using precisely this signal to claim that the theory is conformal. So
you mean which signal? Yeah.
The fact that all the masses scale.
Yes. But
so this is an indication that it's not so. It's just that they might be in the large mass region.
Yes. So what we predict is that Dilaton chiral perturbation theory predicts this large mass regime, and if Dilaton chiral perturbation theory is the right description of these data, we have still chiral symmetry breaking, but still you can see this hyperscaling. Okay, so it's going to be one of the points that I'll mention at the end. But this might be an explanation why it is so hard to know on which side of the conformal cell you are, right? Because the theory can mimic conformal behavior on the other side. Okay, so I don't know where I'm with time, but let me just, for people who know about staggered fermions, I'll say something and the rest of you should just ignore it, okay? This shows phase splittings of staggered fermions in QCD. So what you see, so each staggered fermion, so one staggered fermion produces 4 quark flavors in the continuum limit. They're often referred to in the jargon as tastes rather than flavors, for reasons I won't get into. And the remnant SU4 flavor group on the lattice is broken to a discrete subgroup. And so the pion multiplet that you expect for a theory with 4 flavors, or in this case with 8, splits up into a bunch of different pion masses. One of them is exact. There's one exact chiral symmetry left. So that is this pion here. So the pion mass squared is indeed nicely linear in the quark mass. And then all these other guys are offset by a finite amount that depends on the lattice spacing. So this is an A squared effect. Okay. But the splitting here, as you can see, does not depend on the quark mass. Okay. This is the same. These are the splittings. So these are not the masses themselves, but the splittings as a function of the quark mass calculated by lat KMI. And you see that the splittings there depend very heavily on the quark mass. Okay. And that is again because of this extra tree-level dependence on the quark mass that you can get into the system through the expectation value of the Dilaton field. So there is a way of extending Dilaton chiral perturbation theory to include these lattice spacing artifacts. It's called staggered chi-Peter, so it's Dilaton staggered chiral perturbation theory. You can work it out. I'm not going to do it here, but these blue curves are fits to that version of Dilaton chiral perturbation theory. So what we see is that tree-level Dilaton chiral perturbation theory explains these splittings very well. So this is kind of a technical feature of these lattice simulations, but it's nice because it gives us another way to see whether Dilaton chiral perturbation theory works or not. So in some sense, it's turning a bug into a feature. Right? Okay, so it's another indication that we're maybe on the right path for understanding how these theories work. Okay. So then let me get to the open questions. Okay, so all these simulations are in the large mass regime. Okay, if you take the LSD data, which are the ones at the smaller quark masses, so they're hopefully closer to the chiral limit. Okay, and so maybe I can go back to. You see here, there's the physical F pi is the chiral limit F pi times this factor e to the v. In the large mass regime, this e to the v is a large factor. Okay, that means that if you fit this to the data, this is going to be much smaller than the F pi in the actual simulation. Actually, the F pi is in the actual simulation. I think I had them here. They're of that order. The F pi that you would get in the chiral limit is this very small number, and because it's a very long extrapolation, it comes with a large error. Okay. So these are the values of F pi in the simulation. This is the value in the chiral limit. Okay. So this already tells you if you want to do simulations at a small quark mass to verify the small quark behavior, okay, your F pi times L would have to be still of order 1 or larger. Okay. So that would require gigantic volumes. So this is not easily doable, right? So that's what I'm saying here. Okay, so as I said here, it's a very long extrapolation to the chiral limit. And actually, this is just a fit error, okay? But one thing that there's a systematic error because of a long extrapolation that could change if you would include NLO effects in the chiral Lagrangian, okay? Because if you have a very long extrapolation, higher order effects can have a large effect on a very long extrapolation. Unfortunately, this is not something we can easily do because we would need a lot more data to fit NLO Dilaton chiral perturbation theory. We're looking at how, with my student, I'm looking at NLO corrections in this theory, but it's going to be very hard to say much more about it. So what I'm saying is that this is just a fit error, but there's a systematic error that comes with a very long extrapolation that might make this 100% error, right? So it's very difficult to see whether in the chiral limit this theory actually has this scale, okay? And that again goes back to this point that it's very hard to see on which side of the conformal sill this theory is, okay? Because it could be that this is really just a mass deformed conformal theory, that because of the large mass, you see pionic-like states, okay? But they would disappear if it would be able to go to the chiral limit. And so checking this small mass regime is going to be very, very hard, okay? And so that's what I'm trying to say here. We are trying to look at higher orders and this to see whether we can get a little bit more of a handle on this, but it's going to be very hard because there are so many constants that show up at the next order. And so we're not going to have enough data to really fit it, but hopefully we can learn something, okay? And so even though we have assumed that this theory is on the chirally broken side of the conformal sill, okay, and Dilaton chiral perturbation theory at 3 levels seems to describe this well, okay, it doesn't mean that we know for sure that we're on the broken side of the conformal sill. It could be that we are actually on the other side of the cell, and this theory is kind of faking, the theory that we think it is. Okay, and so we're hoping to, by playing around with higher orders, to get a little bit more information about it, but it's basically a big open question. Okay. So let me stop there. There's much more that I could say, but
Okay, thanks very much.
Any more questions?
Questions? Maybe from. Can you unmute yourself, Maarten? In case somebody asks. No, sorry. Just put your volume on, because if I do it, there will be some echo.
Oh, okay. So I should.
I think it was already on.
It was already on.
We were listening to you.
No, it's in case somebody asks questions from out.
Okay, let me
The volume, yeah.
just turn my volume up.
Yeah.
Is what you want to be.
Because we
So,
cannot hear questions
Oh,
from
I-
the audience here.
so I hope I did that. I hope that somebody is not asking a question and not being heard.
So what's the scale of what is large mass or not? I don't remember. So people doing the simulations, can they know what to do?
No, I don't think so. So there's this, right? So
Yeah.
it's whether this thing is large or small. And so there's this is a dimensionless parameter that measures the distance to the conformal window. So there's this scale M here, which is this combination of low energy constants. And so, of course, from the fits, we can say something about what F pi is in the chiral limit, what B pi is, and so on. The Dilaton sector is harder to have information about because of what I showed here, because of this. So here, this doesn't add much information to the fit because of the large errors. It says that the fits are consistent with the Dilaton being what it is, but we don't get much information about parameters that you can only get from that sector. And so, for instance, in the case of the lat-KMI data, we didn't even fit because they also measured the 0++, but it has even larger errors. So there's the fits are really these are the fits that give you information.
The difficult thing, I think, is because even you mentioned there is only one single lattice spacing. So to know where to do the simulation of this theory.
Yes.
What the value of the data
Right.
you have to do.
Right. Yes, they
That's like
they kind of guess, and I would love to have another coupling because then, first of all, we would start seeing whether there are scaling violations, and in principle, there are ways to include those in chiral perturbation theory. For instance, you could test those space splittings. I mean, they work beautifully, but it would be very nice to see that.
certainly the window in which you will see this thing will depend on age strongly.
Yes, yes. There's no. I mean, for instance, here, this is expressed in lattice units. This is expressed in lattice units, so it'd be very nice to see that at a different lattice spacing. Yeah, and the unfortunate thing is that so there are two simulations, lat-KMI and LSD, but they use different lattice actions. If they would have used the same lattice action, then we would have two lattice spacings. But now I still don't know. So
in the first plot that you've shown for the hyperscaling, there was a constant behavior from the other group from LSD.
you mean the very first slide?
No, but you don't need to go. So it's
Okay.
just a comment. So here, F pi goes basically to 0 in the chiral limit, right? In the right plot.
Right, right.
And
But this is in terms of the lattice spacing.
yeah,
right?
but
So
when it appears in the denominator, in the plot on the left,
right.
this doesn't go to infinity. So it's simply saying that m pi squared is going much more faster to 0 than f pi squared. And this is
Yeah, so in principle, this somewhere here is the small mass regime. Right, and notice the scale here, right?
Yeah.
So this is from 10 to 20. Right. So if I plot this back to on the scale of the first plot that I showed, where I showed this ratio, this becomes very, very flat.
all right.
Right. So if you extend the plot to down here is where 0 would be. So these points are all in the flat regime, in the large mass regime. And then yes, eventually, as Stalin was asking, this theory, when you make a quark mass very small, the Dilaton has to decouple because you keep the conformal cell distance to the conformal cell the same. Okay, so the Dilaton is in the chiral limit has a non-zero mass. Okay, and so therefore this thing will have to start following the square root behavior. And so that is what this blue line predicts, the square root behavior in this region here. Okay, but if you plot this on a scale where the 0 is here, these points would all be up here, and you don't have the curvature in the region where you would check the square root behavior. Right, so these points, these are exact fits. This is not hyperscaling fits. So there is some prediction of deviation from hyperscaling, but it's only a little bit. These data don't help small mass regime. Maybe the misleading thing here, if you see a plot like this looks like a square root, in QCD, but then the 0 is here.
Yeah, yeah.
Right.
So this is very far away still. Questions?
And also,
You have two sources of conformal symmetry,
yes.
the mass, the fermions, and the fact that the glue and beta function is not exactly. Why do you work in a framework in which you have the two sources of symmetry making always in front of you? Why don't you just go to the Chiral limit from the start?
Oh,
Because you want to compare with lattice simulations, which
yes, exactly. Yes. And a lot of simulations cannot be done in the Chiral limit.
because you are working with two simultaneous, two
Yes.
yes. Sources of breaking.
It would be nice to
just
be able
going to one. Very simpler.
Yeah. So the two things. So there are two sources of Chiral symmetry breaking or scale symmetry breaking. You would like to vary them both, but varying NF is a lot more expensive. It's a new simulation for every value of NF. Whereas in principle, in the same simulation, you can, first it's also a new simulation, you need to update quark mass. These are then alpha fermion simulations, of course. So that's also expensive, but it's way more expensive to repeat this whole game for other values of NF. And so the handle that we have given to us by LSD is, and lat K and I, is the dependence on the quark mass. So we're interested in applying our effective filter in such a way that we get the dependence of the quark mass. But it's relatively indirect, right? Because not only is the quark mass the thing that we have, but that's being varied in those simulations. And then we're looking at pionic quantities, not at the dilaton itself very much because of these large errors. And so the information that is useful is that the dilaton is more or less degenerate with the pion mass within errors. And that's already what you don't see in QCD. Okay? So also in QCD, it's very hard to measure the 0++ state, actually even harder because it's unstable. But we know in lattice QCD simulations that what's called the sigma there in the 0++ state behaves like we expect from QCD. And so it's and by the way, what you can do is one question you can ask is in QCD, how far is QCD away from the conformal window, right? If it's close enough to the conformal window, this formalism should apply. So you can calculate with this formalism the decay rate of the sigma into two pions. You get a prediction from Dilaton perturbation theory. It's by at least a factor of 10 off in QCD. So QCD is far away from the conformal window. There's no way that QCD fits into this picture.
But is there a regime of large masses where you could see similar in the quench, close to the quench?
You mean in QCD? Well, in QCD, there will be no large mass regime, right? Because there is not this other small. So from looking at the sigma decay width, we know that Dilaton perturbation theory doesn't apply. So there is no small parameter C1. So we don't have another small parameter. So your mass is large, then that Chiral perturbation theory doesn't apply, or it is small, and then standard Chiral perturbation theory applies. So there's no equivalent to the large mass regime. So that's a new prediction of this effective field theory framework. And so technically it's unfortunate. Not surprising if this is true, it's not surprising, but also unfortunate that simulations are in this large mass regime.
What's the status of the fight?
Oh, I'm not even. Well, the fight is a typical Hungarian fight, I would say. And I read papers by Julius Kuti, and I'm reading papers by Anna Hasenfratz, and I'm convinced of every paper. Once I've read it, I think this is beautiful work, and what they say is right, and then I read and
But the debate is about NF equals not 8, no, it's also 8.
Well, so the question that they're trying to answer basically by looking at the beta function itself, right? So you want to see whether the beta function has a 0 or not. And so as a function of NF, so they simulate NF equals A, and so they haven't done extensive spectrum calculations. Otherwise, we would have the spectra for all of these theories, but the beta function only is, of course, less work than doing a full spectrum calculation. And also the setup is different, right? Because you do Schrodinger functional or gradient flow. And so there's a very, you know, the demands on your lattice parameters are very different. And so they measure these beta functions, they try to identify an infrared fixed point. Then, of course, the question is, once you find an infrared fixed point, are you close enough to the continuum limit? Or is this a lattice artifact continuum fixed point? So it's a very difficult game because you're trying to simulate theories at strong coupling. And you want to be sure that strongly normalized coupling and not strong bare coupling with a big lattice artifact. So I think that's essentially what the fight is about. So everybody agrees that this is hard. But so I think Anna would, I don't know, Anna would not even exclude, I think that NF equals 8 is conformal. Whereas Julius thinks, I think, that it cannot be conformal before NF equals 13 or so. But
I mean, Anna and collaborators thought they had found
yes,
the place where the beta function was
right,
vanishing, and then the other group redid the calculation and found it was away from 0.
right, right. All I can say, they're both very serious people who, you know, so I have no judgment of this.
No, it was just, I didn't follow lately.
Right. I think this will be constant in time for a long time, so you don't have to follow it every year.
Okay, so there are further questions. Let's thank again Maarten.
Thank you for listening.